Today we're going to be looking at series resonance. But as usual, I share a thought with you this morning, and it comes directly from the scriptures. Whoever quarries stones may be injured by them. Whoever splits logs may be injured by them. In other words, and I always try to make them relevant to networks. If you're going to deal with networks, then in terms of what is required, what is involved in the work, you're going to be impacted by it. That's the bottom line. So whatever you're doing, you're going to be impacted by it. But the kicker here is that if the axe is dull and its edge unsharpened, more strength is needed, but skill with skill will bring success. So we can't come to networks with a dull axe, meaning we have to be on top of the theory. We have to be on top of the material that is presented. Once you're on top of the theory, once you're on top of practicing and getting that cutting edge, so to speak, no pun intended, things will be a lot easier. Okay, the amount of effort that we put in would not be as great. So that's my thought for today. Now we can get to networks. Now, much of what I'll be presenting is already in the printed notes, so I may not necessarily delay a lot on some of these slides, as you already have the information before you. So you just need to highlight certain things and move on. All right. So series resonance, we start with a series RLC circuit, which is shown there, supplied by a variable frequency supply. And the impedance, which will be given by Z equal to R plus J XL minus XC. Yes. The magnitude of the impedance be equal to the square root of R squared plus XL minus XC all squared. So in complex form, this is your impedance. Yes. And from Pythagoras' theorem, well, I'm a little distracted this morning. Anyway, we have Z to be equal to the square root of R squared plus XL minus XC all squared. Okay. If we represent these graphically, that is our inductance, inductive reactance, capacitive reactance, and resistance. If we start with the resistance, we know that that would be constant for the frequencies being considered. And here, again, as I said on Monday, we're not interested in skin effect and that sort of thing. We're just assuming that for the frequencies that we are considering, the resistance will remain constant. Okay? And therefore will be a value parallel to the frequency axis. For the inductive reactance, or 2 pi FL, that is our inductive reactance proportional to our frequency, gives us a straight line that will pass through the origin, and we have already established this from AC circuits. The only slight modification from AC circuits is how I have drawn XC, and what we have here, the XC, which is 2 pi FC to the minus 1, it's just a mirror image of what you would have had from AC circuit. So I would have drawn that in AC circuits, something like that. Yeah. All we're doing is showing the mirror image, which in fact is what the representation would look like if we draw it with respect to minus JX. So on the negative imaginary axis. So there's, nothing has changed in terms of what was presented before. Now, there is a frequency all right, which we will refer to as FR, and here is FR. There's that frequency where the inductive and the capacitive reactances are equal. And that is the frequency that we are going to be talking about this morning. All right, that frequency is your resonant frequency. So if we look at this in terms of the reactances combined on the same set of axes. So here I am showing it on the minus J and J, and of course on the real axis, which is your frequency. But if I put those now just on a reactive component versus real versus frequency, the resonant frequency occurs, and that is where XL is equal to XC. Okay? Above that frequency, above FR, we would have, this should be the other way around. So this would be XL is greater than XC. All right? So above FR, so for frequencies above FR, XL is greater than XC, and the circuit would be more inductive. Below FR, heading to 0, the circuit becomes more capacitive, which is what we are highlighting here. However, at FR, the circuit is purely resistive. Okay? But we start by looking at XL being equal to XC. And we said that that occurs at this particular frequency, resonant frequency FR. So if I were to write the two expressions, XL and XC, all right, I get that 2 pi FRL is equal to 2 pi FRC to the minus 1. And if we simplify that, we get FR, the resonant frequency, to be equal to 1 over 2 pi root LC. And students, this is for our series circuit. So the frequency at resonance for a series RLC circuit is given by all right. So this, the early part of the class this morning, we're just going to go through getting all these formulas out of the way. Good. Now, we said that at this resonant frequency, XL is equal to XR, which means obviously that XL minus XC. I don't know what's wrong with me today. Which means that XL minus XC is equal to 0. All right. If that is true, then going back to the equation we showed earlier for the impedance, yep, that equation would now be equal to the square root of R squared plus 0, which is equal to R. So from this, we can make some other statements. All right. One, this would represent the smallest value of impedance of our circuit. So that's the first statement we can make, that at resonance, the impedance is a minimum. And if we have the minimum impedance in the circuit, then it means that the current would be a maximum. So at resonance, we have minimum impedance, and this corresponds to maximum current. Any questions? All right. Now, if you recall, when we were looking at AC circuits, we had that the phase angle phi was equal to the inverse tan of XL minus XC over R. Good? But at resonance, we said that XL is equal to XC, or in other words, XL minus XC is 0, which implies, therefore, that phi would be the inverse tan of 0, which, of course, is 0. So if phi is equal to 0, it means that at resonance, we know P is equal to VI cos phi, and Q is equal to VI sin phi. Yes? This implies, therefore, that at resonance, the phase angle of the circuit is 0. We have already established that the impedance is purely resistive. But we can also state that the circuit will only consume active power. Because if we go back to this, cos of 0 is 1, sine of 0 is 0. So it means that Q would be equal to 0. So what we would have is only active power. So S would be equal to P at resonance. And that power would represent the maximum power that can be dissipated in the circuit. And it's the maximum power because we are dealing with the maximum current. So P, which would be P max, is equal to I max squared times R. Any questions? Any comments? All right. So we move on. So just comparing, and this is somewhat summarizing all that we have just said. All right. We first have the impedance versus frequency graph. So we have our frequency, we have our impedance. For impedance versus frequency, we have at FR, Z is equal to R. Above FR, XL is greater than XC. Below FR, XC is greater than XL. So we have minimum impedance. We have to the right, more inductive, to the left, more capacitive. For the current versus frequency, we have that at FR, we're dealing with the maximum current. But obviously, if you look at the impedance, we are increasing on either sides of FR, which means, therefore, that the current would be falling on either side of FR. So we have at the maximum, and then we are falling on that side, we are falling on this side. Now, just a quick note, these curves are not symmetrical. For obvious reasons. I mean, there's a limiting value up to FR. And on the other side, this goes to infinity. Yeah? So it's not symmetrical. And two, XC and XL varies differently. All right. All right. So with that said, again, any questions? So we're moving on to something else. Anybody? All right. So next, I'm going to make a statement, and then I'm going to make some further derivations from that. And the statement we want to make is that there are frequencies, there are two values of frequencies, all right? And it occurs on either side of FR. However, at the frequency where the net reactance, and the net reactance is simply XL minus XC. All right. And we are looking here at the modulus because, as I said, it's occurring below FR and above FR. Below FR, XL minus XC is negative. Above FR, XL minus XC will be positive. And we did establish was it last week? No, 2 weeks ago, that we always maintain the XL minus XC. All right, we have established that. But we are looking now just at in terms of the modulus. So at the frequency where the net reactance is equal to the resistance of the circuit, mathematically what we're saying is that R is equal to XL minus XC. So if you find the difference between XL and XC, it's going to be equal to R. That's all we're saying. If that is true, then it means that the impedance at these frequencies would be equal to R squared plus R squared, the square root of that. So we get the square root of 2R squared, or the square root of 2 times R. So the impedance is root 2R. It means, therefore, that the corresponding current is going to be equal to E over root 2R, which is IM, since IM is equal to E over R, which we have already established. So it's IM times 1 over root 2, where 1 over root 2, where 1 over root 2 is 0.707. And so I can represent all of this graphically as shown. So we have, at these frequencies, we're calling them frequency F1 and F2. Yep. So at F1, R is equal to XL minus XC. At F2, R is equal to XL minus XC. And they correspond to a current of 0.707 times the maximum current. So at FR, we have the maximum current. When we get to F1 and F2, we have the current being reduced by a factor of 70%. Again, I pause. Do you have any questions? All right. All right. So we move then. We move along. The current at these 2 points will result in a certain amount of active power being produced. And we know that from our AC circuits, we know that the active power is given by I squared R. We know it's dissipated in the resistive part. We had established that already. Excuse me. So the active power is going to be equal to I squared R. But I is equal to 1 over root 2 times I max all squared. So this is the current at the current at F1 and F2. And if we square 1 over root 2, we get a half. Im squared times r, we just established that that is P max. So based on that, it means that P at these two frequencies is given by half of the maximum power. All right? So at F1 and F2, the maximum power is reduced by a factor of 50%. Any questions? Anything I just said that sound clear? Now, I can write a relationship between the power at these two frequencies and the power at the resonant frequency. And the relationship I'm going to write is that the gain, what's a gain in power from I max to I? Obviously, we're using the term gain, but it's really a loss, eh? So it will be P, 10 log P over PM. And this is to give the answer in decibels. So we'll have, since P is equal to half PM, all right, we make that substitution, the PMs will cancel. So we get 10 log a half. Log of a half minus 0.3, 0.30 something, all right? And 10 times that gives us minus 3 decibels. So, couple of things. One, we have the gain at this point being minus 3 decibels. And two, we have that the power is halved at these two frequencies, all right? And because of that relationship, we therefore have these names applied to those 2 points. So F1 and F2, at F1 and F2, we know that the power is halved, so we call them the half power points. At F1 and F2, we know that the gain is minus 3 decibels, so we call that the minus 3 dB points. The other one, we have not really derived anything to provide this name. However, what it represents is the point at which you would consider that the power is not useful. In other words, there will be too much noise. So if you have, and this may be best explained if we think of a radio station transmitting. The frequency of that particular signal would represent the resonant frequency. So if it is RGR 94.5, that is the resonant frequency. However, if you should shift 94.6 or 94.4, you start getting some distortion. That's not so much an issue these days, given that we're dealing with digital signals, but or digital equipment. But if the point is, if you went to 94.6 or 94.5, you start to get some distortion. The signal is not as clear. Why? Because the power output, or the power with which you are receiving that signal, has not fallen. Whether it has fallen below the cutoff frequency is neither here nor there. The concept is what I want you to appreciate. So at F1 and F2, we are saying that the signal below 50% can be considered not to be useful. So we refer to it, or refer to these as the cutoff frequencies. All right? So at these frequencies, at these cutoff frequencies, F1 and F2, yep, And we also refer to them as the lower and upper sideband frequencies. At these two frequencies, if I should find the range between them, that is referred to as the bandwidth of the circuit. So the bandwidth of the circuit would be the range of frequencies between F1 and F2. All right, so we have spoken about situation at resonance. We have looked at the maximum power, the fact that we have the maximum current, the maximum power, the minimum impedance. Yes. We have now moved on to looking at the half power points or the -3 dB points or the cutoff frequencies. Yes. So I pause therefore. For any questions? Anything I've said so far that is unclear?
Yes, sir. For me, the cutoff frequency part, I never quite get that.
That's just another name we give to F1 and F2.
Oh, okay.
All right. So I can call them the cutoff. I can refer to the cutoff frequencies. I'm still talking about F1 and F2. If I say the half power points, I'm still talking about F1 and F2. If I say the -3 dB points, I'm still talking about F1 and F2. You with me? So that's it. Good. So I can use any of those terms, and I'm talking about the same two frequencies. All right. So the next thing we want to talk about is the fact that up front, we said that the inductive reactance and the capacitive reactance are equal at resonance. Nothing wrong with that. It's true. However, what we may not be clear about in our minds is the fact that those impedances can be fairly large. The fact that they are equal does not say anything about their magnitude. Do you agree with that? So remember now, what's the main condition that we spoke about so far in terms of resonance? In your mind, what's the main condition that we have mentioned? Anybody?
Minimum resistance, maximum power.
Go again?
Minimum resistance, maximum power.
And the minimum resistance corresponded to what?
Inductive reactance and...
No, well, it's a minimum resistance, and I went ahead with it, but it's minimum impedance. The minimum impedance corresponds to what?
Maximum current.
Maximum current. Yes. Now, if you have the maximum possible current, and based on what I just said, the inductive and capacitive reactances can be large. Now, if you have large inductive and capacitive reactances, and now you're operating with the maximum current, immediately what you should be seeing is that the voltage across L and C can be very large. You get that? You get the connection? You're dealing with maximum current. But we are also saying that the reactances themselves can be large. So it means that with the maximum current and large reactances, you can have very large voltages across L and C. But because XL and XC are equal and they are opposite, it means that VL and VC will also be equal, but they are opposite, so they will cancel each other. But you must never ignore the fact that VL and VC can be large. They cancel each other, but individually, they are large. Now, having said that, we are now giving you the statement that these voltages can be much larger than the input voltage. All right? And the fact that they can be larger than the input voltage, we look at that ratio in terms of the voltage across LRC with respect to the supply voltage. Right? And that ratio we refer to as the quality factor. So the Q factor is the ratio of the voltage across the inductor or the capacitor. Remember, they are equal, yes? The ratio of the voltage across LRC to the supply voltage. And the supply voltage would obviously be seen across R. All right, so Q is equal to VL over VR or VC over VR. Where, of course, E is equal to VR, and we know that VL is equal to VC. So if we were to simplify this, ladies and gentlemen, if we were to simplify this, what we have, if I substitute for VL, that would be omega L times I. And for R, VR, it will be I times R. So I'm left with omega L over R, because the I's cancel, as we show here. However, remember, all of this is occurring at resonance. So I can substitute for FR, and we have the formula already. We know FR is equal to 1 over 2 pi root LC. So if I make that substitution, I get 2 pi L over R, and then I substitute for FR, which is this. So I get 1 over 2 pi root LC. All right? Which simplifies as shown. The 2 pi's cancel. All right? Now, L, all I have done is to write L as square root of L times the square root of L, which would be equal to the square root of L squared. Nothing fancy. All right? And in the denominator, the root LC is equal to the square root of L times the square root of C. So these cancel. That and one of that cancels. And we are left with that expression. So the quality factor is equal to 1 over R and the square root of L over C. And, you know, where possible, I encourage you just to highlight these formulae that we are deriving, because you're going to use them at different points, okay? All right. Now, remember we said that at F1 and F2, the difference in the reactances will be equal to R. Yes? Let's just take that one step further. This would be XC, and this would be XL. But it's occurring at F1. So that's the lower sideband frequency. At F2, what we know is that XL minus XC is equal to R. So at F2, this will be XL, that's XC. And we show that in the diagram. We show that above FR, the inductive reactance is larger. Between 0 and FR, the capacitive reactance is larger. And that's all we're writing here. So at F1, capacitive minus inductive is equal to R. At F2, inductive minus capacitive is equal to R. Nothing fancy. So we're going to use this to our advantage. Let's just continue the analysis. So instead of writing the 2 pi F1, yes, instead of writing the 2 pi F1, I'm going to write omega, not changing anything. So from equation 1, we have XC1, which is 1 over omega 1C, minus XL1, which is omega 1L. Right? Multiply through by omega. Yes. Rearrange to have everything on one side. Right? Bring everything on the right hand side. So we have omega 1 squared L plus omega 1R minus 1 over C. Don't worry, you soon see where we're going with this. And then we're going to make the coefficient of the square term 1. So I just divide through by L. Again, nothing fancy. All right. Now I can use the quadratic equation. I think we are all familiar with the quadratic equation. Minus b plus or minus b squared minus 4ac over 2a. Yeah. So that's all I'm doing here. And then if I were to bring this 2 into the square root sign, if I'm bringing a half into the square root sign, then it means I'm going to be multiplying by a quarter because the square root of a quarter is a half, all right? So that's all I'm doing with the next step. So I'm just putting everything within the square root sign. And of course, we are dividing R over L by 2, so that's R over 2L. Now what I'm asking you to take note of is the sign. So here we have minus R over 2L from the equation, plus or minus, we have our determinant there, right? Have I lost anyone? So just applying quadratic formula. From this, or since we went through all the details with F1, I'm going to repeat the same process for F2. But as I said, since we already went through all the detail with F1, yes, I'm just going to give you the expression for F2. Right? So we have X minus XL minus XC, same thing. Yeah? And then, of course, we have that as our equation. Going through the same process, you know, bringing whatever to the right-hand side and multiplying through by C and all of that. All right? That's what we went through here. This gives us the final expression using the quadratic formula of r over 12 plus or minus. Again, we have the same thing in the square root. Difference here is that here this is positive. So at f1 it was negative, at f2 it's positive. But both expressions gave us omega 1 and omega 2. So for omega 1 it was negative, for omega 2 it's positive. All right, before I go any further, again, I pause. Do you have any question? Have I lost anybody? All right. So if I then have omega 2 minus omega 1, I'm going to get r over L, because remember I highlighted the fact that one was positive, one was negative. And it was r over 2L. So it means that we're not going to add them. So 2 minus 1 would be r over 2L minus minus. So we get r over 2L plus r over 2L. That's half and half, give us 1. Good? So omega 2 minus omega 1 is r over L. Now, I mean, I'm sure you have seen this technique in math where, you know, just to get to a certain point, 1 is a beautiful number, but we can write 1 anywhere we choose. Because 1 doesn't change anything. If I multiply by 1, I change nothing. But so I'm going to use that and write 1 as omega r over omega r. And I'm going to multiply the right-hand side by 1. So let's do that. So I get omega 2 minus 1 to be equal to r over L times 1, which is omega r. But recall, we just stated that Q was equal to what? VL over VR, which was IXL over IR. The I's cancel. So you're left with Q being equal to XL over R. And Q is occurring at resonance, no? So we look at Q at resonance, where XL at resonance would therefore be equal to omega R times L, which is what we have here. But instead, what we have is that. We have R over omega L, which will be 1 over Q. We clear on that one? There's some little fancy math footworks. Nothing major. So we get omega 2 minus omega 1, omega r over q. What is common about omega is 2 pi. So I can take out 2 pi. And if I take out 2 pi, yes, I would get F2 minus F1. And what is F2 minus F1? We just found that. That's bandwidth. Yes? And omega r over 2 pi is FR. So the next formula we just found was that the bandwidth is equal to the resonant frequency divided by the quality factor. Any questions? No? All right, excellent. So let's march on. I'm going to go back to the same formula that we started out with, meaning looking at XC and XL at F1 and F2. So I'm going to go back there. All right, so let's do that. So there are 4 points which we just established. We know that this is true. We have shown that already. And we know that this is true. All right? But we are going to take a different, or focus on a different area of these 2 equations. Let's note the fact that in both equations, it's equal to R. So 1 over omega 1c minus 2 pi F1L, that's equal to R. And 2 pi F2L minus 1 over 2 pi F2C is also equal to R. So we make them equal. We can clean it up a bit. We multiply it through by C. Yep. Now, one of the things we did not highlight, well, I'll show you here. Remember that FR, we said FR was equal to 1 over 2 pi times the square root of LC. Yes? So if I multiply across, I get 2 pi FR, which we now know is equal to omega R. And if I square this, that would be equal to 1 over LC. So that's how we get to this point. So omega R squared is equal to 1 over LC, which implies, obviously, that LC was equal to 1 over omega R squared. So I'm going to make a substitution for LC. So Thomas, you have this covered already, yeah?
No, sir, just trying to take in everything.
Oh. So you take the picture of what we have already?
No, I have the notes already.
Okay. All right, so making that substitution for LC, LC being 1 over omega R squared, we get that. I just separate those reciprocals from the other stuff. On the left-hand side, if I'm adding 1 over omega 1 plus 1 over omega 2, we're adding fractions. That would be omega 2 plus omega 1 over omega 1 times omega 2. Nothing fancy about that. And on the right-hand side, yes, I got omega 1 plus omega 2 over omega R squared. Again, nothing fancy about that. So since we have this, gentlemen and ladies, what I'm going to drive at is that if we have two fractions that are equal, and it is clear that the numerators are equal. If the fractions are equal and the numerators are, it stands to reason that the denominator must be equal. Does that go? So we use that fact and we are able to say that omega r squared is equal to omega 1 times omega 2. And if we factorize the 2 pi f, what we are left with is that the resonant frequency is equal to the square root of the product of the two sideband frequencies. So you have a plethora of formulae that you have to be familiar with, right? You know two ways about it. Right? So you have FR equal F1, F2, you have that bandwidth equal FR over Q, you have a formula for Q, you have a formula for, well, you know the relationship at resonance in terms of the current and the impedance and the phase angle and the power, right? We have gone through all of that, okay? And having said all of that, I can now pause and say to you, we have nothing further to say regarding series resonance. You have done everything. Now I know that under normal circumstances, this is material you would have spent a couple of weeks going through, right? Whether in high school or in the diploma, if you're in the diploma, right? But we have taken just about 50 minutes to go through this. So I understand that it will take some time for persons to simulate this thing. All right, but I help you over the hump anyway. So this question is in your lecture notes. So I'm not gonna pause and wait for you to write this down. We're just going to get straight into the question. All right, so we have a series RLC circuit, has a 5 microfarad capacitor, 4 ohm resistor, and a variable inductance. Now, practically, the variable inductance will not exist, but for the purpose of the question, we just put it in. Right? The supplied voltage is 10 at angle 0 at a frequency of 159.1 hertz. It says that the inductance is adjusted until the PD across the resistor is a maximum. Now, yes, we know that we have just completed going through resonance. So it will be fair to assume that the question is about resonance, okay? But the bigger question I want to ask, and I'll start with Mr. Henry, Javoy Henry. Mr. Henry, what is it about this question that suggests that the circuit is resonating? Apart from the fact that we are doing a resonance class. What is it about the question that tells you that the circuit is at resonance?
Sir, not sure.
Yeah, I know you're not sure. Hardly
Not
anybody
sure.
in the class is sure, but I still need an answer. It's not about getting it right, I want to hear where your headspace is.
Sir said that, what is it about the question that determines that?
That tells you that it's a resonance question. Yes, that's, yeah.
The fact that it says that it's a series RLC circuit.
Yeah, but we did some series RLC circuits last 2 weeks. Were any of them resonating?
Probably have a AC voltage.
Yeah, but if we put an AC voltage in a circuit, that doesn't mean it will resonate. All right, Mr. Alexander, You have your hand up.
Sir, can you hear me?
Yeah, go ahead.
Okay, sir. Because it says the inductance is adjusted until the PD across the resistance is at maximum. So
Go ahead. Go
the
ahead.
maximum current. So because of the maximum current, we say that XL and XC can also be large, and with maximum current and
Hold on,
maximum.
hold on. You started out perfectly, but you started rolling down the hill when you continued. All right. So it's just the first statement that you made, which is to say that because you're told that the PD across the resistor is a maximum, it means that the circuit must be operating at resonance. Because that only happens if you have the maximum current flowing. And the maximum current can only flow if you have resonance. That's all I need. All right. So the fact that we're dealing with an RLC circuit means absolutely nothing in terms of resonance. The fact that we have variable inductance says nothing. The fact that it has a frequency, again, says nothing. The only thing in the question that tells you it's a resonance question is because of the maximum current across the resistor, maximum voltage across the resistor. So, what's the first thing that we need to do? Is that Thomas? Well, Andre. It's the first thing we need to do.
So we can find that resonant frequency by using the formula 1/2 pi the root of LC.
Okay, fair enough. Mr. Bernard, you have been enjoying the class. That's the first thing we need to do.
Not sure, sir.
Eh?
Not sure, sir.
Well, you were grinning your face off, man. I thought you were enjoying the thing and understanding it.
Somebody come in my room, sir.
Oh,
No, but
I thought it was the resonance that was making
sir,
it.
highly unlikely. Yeah.
Mr. Vassam, it's the first thing we need to do.
Hold on, sir. I'm looking for the question. That's all I was doing.
Okay, man. Anybody? What the first thing we need to do? Because you know, you guys, this is week 11. This is week 11. Or week 10. We're going into week anyway. You guys really have me concerned. Mr. Alexander, what's the first thing we need to do? Let me see if at least one person has learned something from networks. Or I should just sign you all up again to redo the course. Come, Mr. Alexander, what's the first thing you need to do?
Sir, I'm looking over the question, sir.
Why?
Sir, because I want to
No, but that means if you're looking over the question, you don't know the first thing to do. Anybody?
Sir, draw
Sir, we
the
need to
circuit.
draw the circuit.
Draw the circuit. First thing, I'm very deliberate in what I say. You know. So, you know, you're going to go into an assessment with me. And I mean, yes, you know, we spoke about the error with what I uploaded, but did you take note of the fact that just to label the circuit, you got marks? You think you can afford to lose marks going forward? Think about it. So the first thing we need to do is to draw the circuit. There's no question that you will do in electrical networks which will not require a circuit. None. If you believe it will not require a circuit, that means you have just gotten it wrong. So that is 4 ohms, 5 microfarads, and we have L. And we have 10 volts 159.1 hertz. Okay? Okay. So now that I've drawn my circuit, how do I find the value of the inductance? I'll come back to you, Mr. Thomas. Okay, you were way down the wicket playing spin.
So after you found the resonant frequency, we know that
But why would I need to find the resonance frequency?
because we can find the inductance with the formula.
So I'm saying, why do I need to find the resonant frequency?
Because that's the frequency that the component is operating under.
Okay, so how do I find it? How do I find it? How do I find the resonant frequency?
Using the formula 1/2 pi square root of L times C.
Yeah, but isn't there an unknown in that formula?
Yes, sir, the inductance, but the inductance should be equal to the capacitance. Will be equal.
No. It's the inductive and capacitive reactances which are equal, not L and C.
Yes, really. This calculation is wrong.
So I ask the question again, why would you need to find the resonant frequency? And don't worry that I'm asking you, I'm asking the whole class, but I'm focusing on you.
Yes, sir.
What were you told up in the question?
You were given the frequency of the voltage supply and the capacitor value and the resistor value.
Good. And what were you now adjusting in order to get resonance?
The inductance.
Good. So shifting the inductance causes resonance to occur at what frequency?
Oh, 159.
Which is why I kept asking you why you need to find it, because the
It's already there.
159.1 is the resonant frequency. All right. Everybody with me? So from FR is equal to 1/2 pi root LC, yes? We have FR 4 pi squared F squared is equal to 1/LC, yep. Which implies that L is equal to 1/4 pi squared FR squared C. Calculate that for me, please. What is L? All right, when you guys figure that one out. Next. So the next next part of the question, the PD across each component. How am I going to find the PD across each component? Let me go down the line. What information do I need? So small. What information do I need to find the voltage across each component?
Sir, you're going to need the resistance and the impedance. And not the resistance and the current, sir.
I need the voltage drop across each component. What do I need? What information do I need? If you're going to find voltage drop, what do you need? So Hemmings, what do you need? You're going to find voltage drop. What do you need?
Current.
So voltage drop is equal to current? So Barnett, what do you need? You're finding voltage drop across each component. What information do you need? Pardon me?
We need the current flowing through the circuit as well as the reactance, capacitance, and the capacitance of the RL circuit.
Okay, thank you. So in order to find voltage drops, we're going to need the circuit current. We're going to, well, we have the resistance already, but we're also going to need XL and XC. So Gibbs, what's the circuit current?
The circuit current would be equal to the 10 volts.
Give me a formula, sir. What's the circuit current? What do we find the circuit current?
So V.
Pardon me?
V. Over the resistance total, which would be the resistor and the impedance throughout the circuit.
So then, how do we find the circuit current?
V over R.
Okay, thank you. Why is it V over R, Mr. Denham?
The voltages across the inductor and capacitance will cancel each other out.
Thank you. So it's resonating, so all the voltage is seen across the resistor. So that would be 10 over 2.5 over 4. Sorry. I'm so excited at getting a correct answer. I'm talking rubbish. So that's 10 over 4. It was 2.5 amperes. So you have F, you now have L, whatever L was, you have C. Now, when I find XC, how would I find the voltage across the capacitor? Once I have found XC, what would VC be equal to? Give me the formula for that. Has anyone found XC as it, by the way?
Sir, would it be
Go ahead.
XC times I?
Be a bit more specific.
XC times the current flowing through it?
Well, that's I. Well, I'm sorry. Yes, it is I times XC, but I want it to be a bit more specific. Can't think of it?
No, sir.
Yes, Mr. Alexander?
Sir, it would be the IRC.
No.
R.
No. You're correct, you know, Mr. Harrison. What I wanted to do is to make it a lot more. Yes, Mr. Gibbs?
We're searching for IT search since as it's
No.
a series circuit.
No.
I mean, I maximum.
No. All right. And this is something that you guys need to pay attention.
Would it be I max?
No, it's not about the I max. It's I times minus JXC. So whatever it comes out to, whatever magnitude it comes out to, let's call that VC, it would be then at an angle of minus 90. You can never forget that you're dealing with an AC circuit, and therefore, you know, real and imaginary must always be considered. So for the voltage across the inductor VL, it would be I times JXL. So whatever it works out to, it would be at 90 degrees. And for R, it would simply be 10 volts. Are we clear? Because remember what I said before, VC and VL are equal, but they are 180 degrees out of phase. That is why they cancel each other. If you're unclear, this is the time to raise your hand. It's not getting easier from here on in. All right, so no queries. So we move to the next question. So we have here a series, RLC series circuit. In this instance, you're told that the resonant frequency is 2 kilohertz and the quality factor is 40. You're then told that the impedance of the circuit at resonance is 30. And we want to determine the inductance, the capacitance, the bandwidth. I mean, this question tests you on every single thing that we went through this morning. So as I started with the previous question, I do the same here. Let me see if any learning has taken place. So I go back to the happy man in the room. Mr. Bernard.
Sir, draw the circuit, sir.
So some learning has taken place, and for that we give thanks. All right. So the first thing we want to do is to draw the circuit. All right. So we have R, we have L, we have nothing really. And we have that this is 2 kilohertz. All right, good. So we have nothing, basically. Well, let's try and start populating this. We look back at the question. We know that Q equal to 40 and Z at resonance was equal to 30. All right, let's go. Where do we start? We want L and C. So let's start with L. Anybody want to jump in?
So we could use the formula, the Q factor formula, omega R, sorry. This is FR.
What are we trying to find?
We're trying to find the inductance. So
Okay.
the quality factor with the quality factor formula with inductance is, let me just double check.
But that also
Is
have seen it, doesn't it?
Yeah, 1 over R L over C.
And we have 2 unknowns there.
Yeah.
So where do we go?
Omega L over R, sir.
Huh?
Omega R L over R.
All right, so we have that Q is equal to omega R L over R. We want to still have 2 unknowns, Mr. Hopkins. How we get out of this one?
Wouldn't the R be equal to 30 ohms because at resonance?
Absolutely. I just want you guys to think a little, you know. It's not that hard. I just want you to think a little. Good. So because at resonance, Z is equal to R, it means that Z equal R, which is equal to 30. So we have the value for R. So we can rearrange this to find L. So L is equal to RQ over omega R, which will be 30 times Q, which is 40, over 2 pi times 2 times 10 to the 3. All right, whatever that works out to be. If you note, I'm not giving you the answers because some persons here are not doing the work. They just wait on others to give the answers. So you all go sit down and figure that one out. So that is the value for L. Now we can come back, Mr. Thomas, to what you said, where Q is also equal to the square root of 1 over R and the square root of L over C. Agreed?
Yes, sir. So we can transpose to find C for this now.
Yeah. So you have L, you have C, so you can find, you have R, so you can find C. All right? So C is equal to QR squared over L, the reciprocal of that. Mr. Bernard?
So we can ask that question, sir.
Mr. Thomas has caught your issues, man. I'm having a happy class, though.
Sir. All right,
yes,
sir.
Mr. Bernard.
So if the capacitive reactance and the inductive reactance equal the same, sir.
Yeah.
If we have the capacitive reactance here, so we can just transpose the formula and just find inductance.
Again?
All right, for example, them give us a value for a capacitor, right, sir?
Did they?
We find the capacitive reactance, sir. Since the
When?
capacitive react. No,
Whoa. When did we find that?
No, I'm asking a question, sir.
Okay.
All right. We just found inductance, right, sir? So we can find the inductive reactance.
Yes.
And since reactance and capacitive reactance is equal the same, sir, we can just transfer 1/2 Weber C to find capacitance, sir.
Yes.
Okay.
But tell me something now. You prefer go through all of that?
No, it's just a question, sir.
Than to write this?
Sir, you see, because we never fully remember all that right now, sir. The inductive and capacitive reactance remember right now, sir. That's what I'm asking.
Okay, all right. No, man, sure you can do that. But I am using, and I'm happy you asked the question, you know. I'm genuinely happy that you asked the question. Because this is what is going to make the difference. And I think I've said it in other topics. It's what's going to make the difference between the student who completes the paper in an hour and a half and has no problem, and the student who completes 2 questions in the 2 hours. The one who uses this formula will finish the paper, all 4 or 5 questions in an hour and a half. The one who takes the route you just did, after 2 hours, would have completed 1 question. All right?
I use the formula.
No, Mr. Bernard, where I'm going to think something, no. Mr. Me hear you, I may understand. But guess what? You see those formulae? Those are the formulae you came to UTech with from high school. And I know, you know, remember, you know, I am here longer than all of you have been on the earth, you know. Right? I teaching networks before you were all born.
Right,
so I know. That's why I told you from day one that if you're not prepared to allow me to disrupt your thinking in terms of what you know, yes, you're going to have problems, but it's not going to show up until the later weeks. So I understand, Mr. Bernard, and don't feel bad about it. As a matter of fact, I am happy you asked it a couple of weeks before the exams, because if you go in with that type of mindset, I guarantee you, and it may sound very harsh for me to be saying this to students, but I'm guaranteeing you that if you go in with that approach, I will see you in networks in 2023, assuming I'm still alive. That is a guarantee. All right, so we continue. So we rearrange the formula and we find C, whatever C is equal to. All right, what's the next thing we're asked to find? The bandwidth.
FR over Q.
FR over Q.
Okay, so the bandwidth is equal to FR over Q, which this one is equal to 50 hertz, right? Which is the 2 times 10 to the 3 over 40. Next, we're asked for the upper and lower 3 dB frequencies and the impedance at the minus 3 dB frequencies. All right, allow me to do section E before I do section D. So section D wants the impedance at the minus 3 dB frequencies. All right.
Sir, that section E.
Your answer.
All right. Now, how do we go about finding that? Come on, folks. What do we know about the impedance at the 3 dB frequencies, minus 3 dB frequencies?
That the reactance is equal to the resistance of the circuit.
Okay. And by extension, so you're correct. At the minus 3 dB, the net reactance is equal to the resistance. Therefore, what is Z equal to?
Root 2 times R.
Beautiful. So it means that Z is equal to root 2 times 30. Whatever that is equal to. So let's go back now to section D, which asks for the upper and lower so I'm saying now the upper and lower sideband frequencies. Still we're finding that is obviously F1 and F2, right? Look at all the formulae that you have and tell me how you're going to do this one. Come on, folks. Go out on a limb.
Sir, you could I use the quadratic formula, sir?
Use the what?
Quadratic formula which said omega 1 equal minus RL plus or minus root of R over LR squared minus 4 LC over 2 all over 2. And since you find omega, you could find F1 by manipulating for F.
All right, we could. But talk through, Mr. Hopkins. You think you will remember that now, exam? Huh?
Well, no, sir.
There's a lot to remember, do you think?
Yes, sir.
But what you have done, Mr. Hopkins, and I like that. What you did was to stop in the middle. But look at where those expressions brought you. Where did it take you? Where did it bring you? Didn't take you, it brought you there. Where did that ultimately end up? So Hopkins?
Look, I'm looking, sir. 1 second.
No, man, the same formula you just read out to me. That was a means to an end. What was the end?
Oh, so omega 1 would equal minus R over 2L.
No, man. Listen carefully to what I'm saying. We use a quadratic formula, but we were using it to prove a final formula. What was the formula? We use it to prove two sets of formula, you know. What was the first one?
Bandwidth, sir. Oh, yeah,
Bandwidth, which says what?
So, F2 minus F1. Which equal bandwidth and
equal what?
Equal F2 minus F1, sir.
Which is equal to?
F4 over Q.
Good. So that's your first equation. So here you have an expression which gives you a relationship between F1 and F2 and the resonant frequency. Is there, no, the same equation that you mentioned, it also brought you to another place. What was it?
Bandwidth equal FR over Q.
Yeah, man, that's the first one he just gave me. But what other expressions did you end up with F1 and F2?
FR is equal to the square root of the product.
Absolutely. So the next, so the first equation was that F2 minus F1 is equal to FR over Q. So that's one. And then you had that FR squared was equal to F1 times F2. Isn't that so? So how many unknowns do I have in each of these equations? How many unknowns do I have in each of the equations?
Two.
Two. And how many equations you have?
Two.
So you know, all right then, man. So we have two unknowns, we have two equations. We solve them simultaneously, no matter how the equations look. Because we are engineering mathematicians. That's why you do eng math before you come to me, right? So you have these two equations. You have FR, you have Q. You have, well, you have FR and you have Q. So F2 minus F1, we know is equal to 50. Yes? FR squared, we know would be equal to 4 times 10 to the 6. So it means that we can solve these simultaneously using substitution. Do I need to solve this? I pack up my pen already, you know, because I'm sure that I don't need to. Right? So we solve these equations simultaneously. Write F1 or F2 as a function of the other and substitute into equation 1. And then you'll get a quadratic equation. Whoops. All right, you get a quadratic equation. Sorry about that. All right, you'll get a quadratic equation, which you'll then solve. Obviously, from that quadratic, you're going to get a positive and a negative value. But you can have a negative frequency, no? So it means that you'll take the positive value. All right. That's it for series resonance. Well, no, not totally. I have a couple of things that just 2 more slides I need to look at. So those who are interested and you have gone through the values, I think the answers are in your I know the answers are in your yeah, the answers are in the notes, so you can just access that. All right. Okay, so we wrap up this afternoon, talking about selectivity. And I mentioned it earlier because I was talking about the radio station, right? And saying that you know, when you're on the particular frequency, that is the resonant frequency for the station. But as you move away from that frequency, you're going to start getting distortion, right? The ability of your circuit to select a particular frequency and then discriminate against the frequencies outside of that is known as selectivity. And so in terms of transmission signals, right? And this is from an analog standpoint. You're going to, in that sort of setting, try to ensure that the signals that you are transmitting are such that, you know, they fall within a very small band. And so you're now going to say, all right, you need your bandwidth to be what? To be narrow. Because if your bandwidth is spread too wide, let me think of, all right, think of which station is loudest now? You have hot, is it Hot 102? No, not Hot 102. The one in Montego Bay. Anyway, it's at 88.1. Right? So their frequency is 88.1 megahertz. But then you have TBC, which is at 88.5. That's just 0.4 megahertz. So if they were operating at, you know, having wide bandwidth, then they could easily distort what is happening at TBC. You guys, I mean, maybe one and two of you are in the room who may be familiar with when IRFM came on air. But IRFM had a warm time. Why? Because those other stations were not too keen on this new kid to come on the block. And they were going into a niche market. And because they were young and transmitter not as powerful, other people with more powerful transmitters would simply cause their bandwidth to expand and crowd out poor IRA, right? So you'll be listening IRA, and in a few minutes, all you hear was all the ash in the world, right? But to do that, they had to reduce their level of selectivity. And to do that, they also had to reduce the maximum power. So their curve would then flatten. Now I'm saying all of this because the next things I'm going to show you would highlight the importance of selectivity. All right? So discrimination becomes more pronounced with reduction in losses. And this loss that we're talking about, yes, is having a smaller resistance. So you reduce the amount of losses, actual losses that occur by having a smaller resistance. With a smaller resistance, if you go back to the circuit, that the equation we gave you earlier for quality factor, if R is smaller, it means that the quality factor will increase. So selectivity, yeah, will be a function of quality factor. And from what we have here also, you're seeing that the quality factor would increase, or an increase in the quality factor is the quality factor, let me say that like this first. The quality factor is a function of the bandwidth. The smaller the bandwidth, the higher the quality factor. Yes? L and C, they are the ones that are going to ensure or determine what FR is equal to. We have already established that. FR is equal to 1 over 2 pi root LC. So the values of L and C will dictate FR, but R would dictate the quality factor. All right? So graphically, this is what we have. That graph at the green one is showing a narrow bandwidth, which means that your R will be smaller. And as we increase R, we are getting a lower quality factor, but the signal is spreading further and the maximum current is getting smaller. So in other words, if you were to try to crowd out the signals next to you, it means that your output power would also fall. So if that was the intention, the power at which you're transmitting would also fall. All right, so that is it for quality factor, for selectivity. Now you know that. Now we can end. Next time when we meet, we will discuss parallel and series parallel resonance. All right, let me get the register.